All right, once again, welcome to the lecture number 29 of the deep learning course. And in this session, we are going to talk about the three important concepts, and they are actually related. The name is a Boltzmann machine, restricted Boltzmann machine, and belief networks, especially deep belief network. So you may have heard about these concepts, and you may be aware also. But just for the sake of completeness, I have brought these topics. They are very general and very important topics. So initially, what happened that when at the initial time the I think the neural network was proposed, as we have discussed, around 45 or so, 1945 or so. At that time, the big news channels have actually covered that the something has been discovered into the computer science domain that would be that is going to lead towards the human computer vision system and human conversation system. All these things would be possible. So way back at that time, people were thinking that things were possible, but we have seen that it was very difficult to train, and that's why for a very long time there were no progress, and even for some time people said that it has died and new concepts are needed. And it was not very far away time. Very recently we have seen all these things, and but after that the improvement happens very fast, and nowadays many very good architectures are there and we can solve it. In between the time when the people were trying to find out the right parameter, there was a very important concept that came, that is called that energy based model. They wanted to say about something about the energy of a system. So using energy of the system, they can do multiple things, and they were able to actually progress something. But let me tell you this thing, that it is my own feeling that energy based model came as a rescue at that time when something was not able to be done. And people were talking about this for very long. People were prominent on that, but now deep with the invent of the deep learning, people are actually not talking right now, not talking much about this. But in the future, I think that this would again going to come. Why I'm telling this? Because what happens now, the most of the time when we talk about the learning, so neural network based system learn using back propagation. Back propagation is some idea that people want to explore, but if we want to relate it with how the humans learns, so human may not be learning into the same way. Okay, we don't know that whether we learn something and we see the same thing 10 number of times and 50 number of times and then we iterate. It is not like that. Our brain is actually working on these kind of concepts. It is my own understanding is that our brain actually works in this particular way that we are going to discuss today. So maybe at some point of time later, when, because now it is difficult to make the system that can work on this particular concept, but maybe after some time people would be able to train this thing, and then better systems are expected to come. Make sense? So let me talk about something. Let me give some technical details about these models. Let me start by this saying that let's assume that you have a perceptron neuron, one single neuron is there, and there is some input that is coming to the neurons. Okay, this is what they are. Some input is coming to us. So as I told you that it is a old model, 1982. The name is called the Hopfield network. And here the architecture is this, that you have single neurons, and they are receiving the input from the other sources, but they are allowed to feed their output into the adjacent ones also. Into the next point of time, they are going to provide whatever input they had to this particular unit also. So if this particular unit want to do the processing, it is not like that it is using that which are the things which are units which are actually away. It is also going to use the units which are actually very near to it on the same layer. So it is a kind of sometimes we call it the memory view of the neural networks, where the things are more densely interconnected, and we say that it is a recurrent connection is possible. In this kind of circuit, recurrent connections are possible. We have seen earlier also RNNs, the same we are going to use feed into the same layer. So recurrent connections are possible, and it is called the content addressable or associative kind of architecture. So what does it mean would be clear to you very soon. So if this kind of network is given to you, If this kind of network is given to you, and let me give you one disclaimer also, that today's class may be fragmented. Means initially you may be thinking that I'm not able to understand, but after some time would be make that what is we are going to talk about. Okay. So if you have any confusion, please ask the question. Okay. Maybe immediately you cannot understand, but after some time, when the more things would come, then you can connect them and then you can find out the big picture. Make sense? So this is an energy-based model. What does it mean? That if I give you a neural network circuit, you can find out that what is the energy into this particular system. If I give you a model, you can tell me that what is the energy of that particular system. Just give it a minute. Okay. So energy of a system is defined by this particular formula. Okay. What is this formula? Okay. So let me draw a circuit for you. So let us say that there is a circuit, there is a neuron, there is a neuron, there is a neuron, there is a neuron, there is a neuron. Okay. And there is a connection. So let me say that few connections are there. It's not fully connected kind of thing. Okay. They're not fully connected. Let's assume that this is the connections. Let me put some values also. The weight is 10, weight is 5, weight is minus 10, weight is minus 20, weight is 30, weight is 50, weight is 10, 17. I think 50 is going to be a big number. So 14, some numbers are there. What is this number? 20, minus 20, some weights are there. This is what the network circuit is. Yes, and you may have not seen this network circuit because nowadays we follow different kind of things, but this is a network circuit. Here, assumption is this, that it is binary thresholded. The network units are binary thresholded. What does it mean? That they can have the state 0 and 1, minus 0 and 1. Their state could be minus 1 plus 1. So I can assign some value. Let me just quickly say that let's assume that it is going to have 1, it is going to have 0, it is going to have 1, it is going to have, let's assume 1, it is going to have 0. Let's assume that I assign some states to that. Just for the sake of clarity, let me write a few things more. I say that that this is the state 1, this is the state 2, this is the state 3, this is the state 4, this is the state 5. Okay. So I can say that S1, S2, S3, S4, S5, 5 things are there. And its value is what? 1, 1, 0, 0, 1. Am I right? Any confusion on that? Can I write like this? That this is what my network state is. Currently, if this is what my network is, then its state is this. Yes? All right. Okay. We were talking about energy, something like energy. Okay. So let me once again take it here. Let me put it here at the top so that you can see it. Okay. Now, what is the energy? Energy is defined by this formula. Now we have come to this particular formula. Let me tell you what it is. SI means what is the state of ith unit, and there is a B bias, because you know that whenever there is a network unit, there will be a bias that is assigned to that. For the time being, let's not consider this particular part. Let's only focus on the second part. But the second part says that SI Sj means for all I that is greater than j, SI Sj multiplied by Wij. Why I am taking SI greater than j? So that I do not double count. Okay, if I allow everything to I, connection between I and I is also possible. So this is nothing more than a mathematical or computational trick that tells that all the possible pairs. Okay. One more thing that I wanted to tell, that there is something also important part. These units are binary thresholded and they are also symmetric. What do I mean by symmetric is this, that if I want to find out that what is the weight between S5 and S3, so if it is 10, then S3 and S5, this is also going to be 10. Okay, weights are symmetric. Means what? That there is a connection and there is a weight, it is symmetric. Means both the sides. If I, for example, when I write here that this is a weight 10, means weight between S1 and S2 is 10, and S2 and S1 is also 10. Okay, it is a both side direction. All right, we are talking about energy. Sir, where is the energy part? You are not discussing that. Okay. So energy, let me just go to this particular formula only. I was telling that for now, please don't consider, just leave it for 1 minute. So let us focus on this particular point. For all possible i's, I need the j's which are actually greater than this. So i's, all possible i's are what? Value of I is, I could be 1, 2, and when I is 1, then what is the value of j? What is the value of j? 2, 3, 4, and 5. Am I right? When the I is 2, then it is 3, 4, 5. I is 3, then it is 4 and 5. I could be 4 and then the value could be 5. These are the values possible. These are the only values possible. Am I right? I and j. What is the value of I and j? When you know the value of I and j, you have to find out that what is the multiplication of Si and Sj, and then you have to multiply with the Wij. So let me just write, it is S1, S2, W12, S1, S3, W13, S1, S4, W14, S1, S4, W15, S2, S4, S2, S3, W23. Am I right? करेक्ट करो, मैं गलती करता हूँ. S2, S4, W24, S2, S5, W25, S3, S4, W34, S3, S5, W35, S4, S5, W45. All right. We have an assignment. We also know that there is an assignment. And what is that assignment? So you see that S1 is equal to 1, S2 is equal to 1, S3 is equal to 0. If S3 is equal to 0, so where is S3? This goes. Where is the S3? Here is the S3. So this term goes away. Where is S3? Here all these terms goes away because there is a multiplication of the 0. Because in that particular expression, the multiplication of 0 is there. So they are not going to contribute anything. Am I right? Then I say that S4 is also 0. So S4 is also 0. Where is A4? This is also going to be 0. This is also going to be 0. All other things are 1. So when I find out the multiplication of S1 and S2, it is going to be 1 only. So what is the multiplication? It is what is the weight between them? So weight is going to be how much? How much weight we have? So W12 is 10. W12 is 10. So here S1, S4, S1 and S4. What is S4? S1 and S4 is 0. This, because there is no connection, so weight is 0. So weight is 0, so it becomes 0. 1 minute. It becomes 0. They are not going to be contributed. Yes.
Sir, there is a typo. It was S1, S5, not S4.
Okay. Thank you. Thank you. Thank you. ऐसा चाहिए ना? हाँ. So 1 and 5, then the value is 17. Thank you. Okay, the value is 17. 2 and 5, as 2 and 5, there is 2 and 5. Is it right? 2 and 5, the connection is, there is no connection, so weight is 0. This is 0. And 4 and 5, 4 and 5. How come 4 and 5 have come? Yes, 4 is actually 0. Okay, cancel out. So the total summation is going to be what? Total summation is 27. And in this particular formula, this part is 27. So energy is equal to minus 27. Any questions on that? How to find the energy? Okay. How good it is? This energy is how good? So it is minus of energy. So because lower energy is better. If you have higher energy, then you would not be settled up. You'll be changing multiple things. If energy is down, means what? Things are settled. We want the settled things into this network. So goodness is 27. If so, may I write like this 27? Let me ask a question. And the question is this, that 0, 1, 1, 0, 0. What is the energy of this thing? maybe some value. Maybe this could be 21 or 29. Anything could be possible. So out of all possible combinations, you can find out which is the assignment that is going to give me the lowest energy. Okay, given a circuit, once again, given a network circuit, you can find out that what is the assignment that gives me the lower energy. This is the best assignment for your network. Make sense? That you wanted to learn. Huh? What is the learning? You want to make your neural network into the state where there is a lowest energy. Ultimately, what is the learning? Learning is this the settled network. So we can relate with that here the learning means what? That you are changing the states. You are changing the state, and with respect to the changing of, say, here one side I'm going to tell the states. However, there is not directly there is a how can you go from one place to other, that you have to define that you are changing one bit, and then how can you arrange them into the order? There is no direct order. But if you try to see that one side I put all the states, another side for the energy, so some kind of behavior we can put. There will be some absolute minimum that actually we wanted to reach, and that is if we find out that particular assignment, this is the best learning that we can do. Make sense? Any questions on that? There is also a very important term that is called the energy gap, that actually talks about with respect to a particular network unit. For example, if I want to find out that what is the energy gap of this particular unit, so this would be that because I can put the value to be 0 at 1, so you say that what is the energy when you put the value as a 0, and what is the energy when you put the value as a 1. The difference of these two quantities that you can put into the formula, then immediately you can see that all the other terms become 0, is Pi plus summation of all for all the other network unit, what is a Sj and Wij. So this is what the formula that tells that what is the effect of changing one particular bit. This is the energy gap. Because of this much you can change when you switch this particular network unit. This is the Hopfield network. The idea was this, that the multiple things are there in your brain. They are connected in a very haphazard way. And there is some assignment on that which is activated and which is not activated. And then by this, you actually settle down in some kind of memory state, and then it is your learned state. Okay, idea is very, very philosophically very interesting idea. Okay. This was a general idea that I have given to you. However, they actually have two components, and now we are going to make more sense that there is something called hidden unit, and there is some visible unit. So there are two parts of the network. If we go more technical, Hopfield network has two parts. One is the hidden part, another is a visible part. Into the hidden part, I have written that there are three things, they are connected. Multiple things could be there. You can come up with some architecture. And this is something like that. Please focus. Something like that there is some representation. I don't know that how complex way they are actually connected. So there are multiple units. I'm going to build some kind of architecture over here that is hidden. I mean, nobody knows about that. There are weights. How to find out those weights, we are going to discuss soon. But this is a visible unit. A visible unit says that there are some bits are there, and they are connected with the things into the hidden units in some way. It's not fully connected. I'm not telling that they are fully connected. They're connected in some way. For example, you can see that it's not connected. This is not connected to anyone. It's connected to everybody. Some kind of sparse connection. Everything is possible. It means you come up with some kind of network circuit that is suitable to you. I don't know that how, but you come up with some kind of hidden circuit, and this is the visible unit. What do I mean by this visible and hidden unit? And now you please focus. Let's assume that I have a database. Database contains images. Okay, and images are of only two kind: cat images and dog images. Okay, cat images are dog images. You pick a cat image, and because image is ultimately the number of pixels, you use those many number of units at this particular place, and you put this image at this visible unit. if you put this at this particular place, whether the network would be into the minimum energy state, because you have done an assignment, na? You have done an assignment. Because of this, network would not be into the minimum energy state. So how can I make it in minimum energy state? We don't know. Change something so that the overall circuit becomes into the minimum energy state. Show another cat image, again change. Show another image, again change. Multiple number of time you do. So with all the cat images, cat images, there is a visible unit and there is a hidden part. So all the cat images you are going to show into the visual unit, and it is going to change itself so that its state is actually minimized. Same thing you can do with the dog images also. So there is a on the it's a separate network. It is not the same thing. Two separate models, because it's a model, na? So here you are going to show the dog images. Network is going to settle up to the absolute minimum value, and then network has some property. Now I have a very important question, and that you can answer very easily. I have a new image. I don't know that whether it is a cat or dog. Understand? I am going to feed this to here. I am going to feed to the here, and try to measure that what is the energy of the network. So where, if it is a cat image, let's assume cat image, where the energy would be lower of this unit or this unit. Let me call it A and B. A and B. Okay. If it is a cat image, let me tell you. Let's assume that it is a cat image. Where the energy would be lower? A. Where the energy would be higher? At the B. So if I show you the dog image, then the energy would be lower at B. Have you seen that we have developed a model that can learn something, that can tell something meaningful? Okay, so this is how we can find out the classification. We can do the classification. Now let me tell you more interesting things. Let's assume I don't know how that I have generated this image. I have not taken the image from the things. I have generated in some way. Once again, I'm telling that I don't know. I don't care. Somehow you have created image, and now you are going to feed this to this system, and this system try to find out that what is the energy. If the energy is below some threshold, looks like that there is a cat. I have generated in some way, so it's a generative model also. Okay, you somehow generate something, provide to the system, and if you have actually understood that, okay, because it looks like that it is a good image, because system is going to tell me that with a very high probability that it is a cat. Now you can understand that somehow we have to assign some notion of probability also, that given the image, what is the probability? We would quickly come to that how to assign a probability with this notion. So you understand this particular part, that we can be generative also. We can generate something and then we use this particular network to tell that should I pass in on or not. So there is let's assume a random generator generating multiple things, but feeding to the system, finding out the energy. And if somewhere you find out that energy is suitable, you can tell here is a cat, here is a dog. All right. Very interesting thing I am going to tell you. And this is called the content content addressable memory. There is something called associative memory. You may have heard computer architecture class. What happens, for example, if you are searching something, you have not all the information, few information you have. कुछ search कर रहे हैं आप, only few information you have. So let's assume that there is a representation. In this representation, there are neural networks. There is some representation, feature representation. Actually, they are feature, na? Whatever I'm going to tell, they are going to represent in some way, some feature way. They are going to represent that. So let's assume that there is some representation, and partially, only for some of the state, the value. You don't know the value for all of the things. You know the values for some of them. Means partially you know about the data. What is the problem? Because you know that the minimum state, if you use the partial information and bring the system down to the minimum energy level, all the things which have been missed, they will be there. Let's assume the network is properly trained. So if I if I specify some of the values, for the remaining value, the network would automatically fill, because you know that this is the value on which I get the minimum thing. So he would be able to tell that what the complete information. Given some information, it can tell you the complete information. Content at addressable memory. In the memory, only few things you are going to specify, and then it is going to search that complete content. What is the complete content? Understand? You are only going to specify some things, and this kind of network can tell you where is the complete thing. What is the complete thing? Because you know that the minimum state, if it is properly trained, minimum state would be achieved at some fixed thing. So you can go and find out that on this particular value, I'm going to have the minimum thing. Here, once again, here, as I told you that when I supply the cat images at this particular place, so I get some kind of representation over here that how the cat images look. So we can think that it is a very higher dimensional space, because we can put more things. Now, who is going to stop me? I can put the many network units over here. So if there are 10 things are being input here, I can put 1,000 things, no problem. 1,000 different things I am going to devise. So I can think that here hidden unit is going to be the higher dimensional representation of the same thing. All right. So now something comes that is related to the training. So the training thing says that 1 upon okay. Training actually involves, because we don't know that what is going to happen. So there is a notion that that, for example, if I'm focusing on this particular unit, the value could be 0 or 1. Should I change it 0 or 1 or not? Because I have to do multiple things, multiple times, multiple iteration. I have to find out that what is the best value. So if the value is 0, I can make it 1. If the value is 1, I can make it 0. I can toggle it and try to find out into the network that what is the best value. So there is one idea that says that if you keep changing everything, then the dimensionality of the learning space becomes very high, and you would not do the things into the reasonable amount of time. It says that if you want to change this particular thing, so there is a probability associated 1 upon e to the power minus delta ei divided by t. Probability that you are going to change this particular ith unit from 0 to 1 is going to be related to this particular formula. This is very similar to sigmoid 1. You know that if the probability is high, it means that you should change it, otherwise you should not. There is also a term called T that says that that actually governs that how frequently you are going to change. Initially, what happens that initially you should change the network parameter way more frequently, but as the learning has happened, then you should not change much the parameter. Initially you can change, but after that you should not change, because then the system would be taking long jumps and it would be a problem. There also into the, when you do gradient descent, there also you do the same thing. Initially you take the larger step, but after that you take the smaller step. So T actually represents that what is the temperature right now, and it is just a systematic name, okay, given some fancy name. It is just a value that what is the time, you can think. If the time is high, no. If the temperature is high, initially the temperature is high, after that temperature becomes smaller. Temperature becomes smaller means there is some value that diminishes its value. Then the learning rate actually diminishes. You can think like that. And if you use this thing to update this value and search into the space. The idea is also called the simulated annealing. Sometimes people call it simulated annealing. Means initially you are taking the larger step, but after that you settle down and take the smaller step to reach to that particular position. So the basic idea is this, that when you want to find out the parameter, you initially can change with a higher probability these parameters, but after that you take with the lesser probability, you actually change the parameters. So this is the overall idea. There is another very important concept that is called the Boltzmann machine. So this was an interesting idea that has brought multiple things to our table. But as you know that training is not easy task. And we have not talked about anything about the training. So training is actually very difficult, because when you connect the things into the very different kind of thing, it is very difficult to train. Yeah, Christian.
Wow. In training, do you be only changing the weights or the states also?
States.
The weights will remain fixed.
Weights and both the things we.
We'll update weights using backpropagation.
No, not the back propagation and
So
not.
how we will change?
Yeah, we would try to reduce the energy. We are going to talk about that. Can you explain the recurrent connections part, the initial diagram? Okay, so sorry, Ruchir, I had not seen this. So actually, the idea was this, na. So it's just see here. Okay, here hidden units are actually connected in any way. So earlier in our setting, what happens that we actually in general neural network setting, we actually feed forward, do a feed forward kind of thing. Okay, but here I'm telling that things which are here, they can be related to, they can be connected to other units which are inside. So this thing is, I'm going to call it a recurrent unit, and this is possible because here, if I in this particular diagram, you cannot make it anything that there is any layer. In particular, this particular diagram, is there any layer? No, there is no layer. Things could be connected in very haphazard way because it was initial idea. People were thinking that our brains are also connected in that way. Brains are not inside the layer as we portrait our machines. Our brain is not layered brain. Okay. Does I answered your question, Richard? Understood? Okay. So now let me tell you that there is something called Boltzmann machine, and it actually simplifies the learning process by introducing this particular thing that it says that there is a probability associated with how the visible and hidden things are related, and now you can start thinking something like that visible things are actually my database things, and this is going to have the understanding of that particular thing. Okay, it is going to develop some understanding of that thing, hidden thing. So visible things from the database, for example, we have seen that cat images I'm going to feed over here, and it is going to make sense of that, somehow find out the right parameters. So there is a relationship between them. Okay, there is a relationship that there is a hidden unit and there is a visible unit. What is the relationship between two things? So Boltzmann says that the relationship would be something proportional to what is the energy between these two things. Something would be related to what is the energy between those two things. So a few minutes back we have talked about that there are multiple states. Okay, state assignments. There are multiple state assignments because I told you that S1, S2, S2, it is a vector, and on this vector you can do any kind of assignment. So let me say that these are the all states that are possible. And here what I do, I randomly pick this particular thing and apply update with some probability, as we have seen that the update is going to happen with this probability. And if I update, I would reach to this particular state. I pick this thing, update, I reach to this particular state. I pick this, update, I reach to this particular state. I do multiple number of times, sufficiently number of time, infinite number of time. What would happen? You can measure that 50% of 10% of time I reach to this particular state, 5% of time I reach to this state, 2% of the time I reach to this state, like that. You can come up with this kind of probabilities. After sufficient number of experiments, you would initially, when we start, there will be kitni baar aap kis state mein ja rahe hain, that is going to different. But after some time, you would be fixing that, okay, most of the time I'm going to reach to this particular place. Okay, the probabilities are going to settle down. This place, you can say that this is the thermal equilibrium. Anything they are bringing just to confuse. Okay, so it is, they tell that it is a thermal equilibrium state, that where we think that what are the all the states and what is the probability. So highest probability one is the better one. We want to be in that particular thing because it is dependent upon the energies, and we can tell that this is the best state for us. Once again, if you want to find out, this is nothing new, that if you want to find out what is the energy given some hidden state and visible states, so you see that what is the summation of the BIs at the visible state, summation of BIs at the hidden state, and then what is the energy between the VIs and VI, HIs and HI, and VI and HK. So this formula is actually a long formula, just to confuse you. and you would be more happy to see this particular thing. If I want to find out the energy, what I would do, the same formula, very simple formula. For every unit, you are going to see that what is the state multiplied by the weights between them. So I can divide them into two parts. I can find out the summation for hidden units and so find out the visible unit and then add. They are going to give the same value. Now, ultimately, if I give on the complete network, they are going to give the same value. On the cross connections, if I ask that what is the connection between them, what is the summation between them, and what is the summation between cross terms, ultimately the same formula. It's nothing new formula. The same formula. Do you appreciate this particular formula? Here it wanted to tell that if you consider that visible units and hidden units are different, then you can think that what is interaction in between, what is interaction over here, and what is cross interactions. So these are the three terms. Hey, who is able to understand? कौन समझ पा रहा है? हर कोई? ये इंटरेक्शन विजिबल जो विजिबल में है, ये इंटरेक्शन हिडन के बीच में है, ये क्रॉस भाई वेट है सर, वेट होंगे सारे समेशन है. This is again the part from the visible, and this here minus sign has been taken out so that because in this formula there was a minus. All right, so what is the probability of VH? If you find out that there is a E into V is something that I have just fed into the system. V is something that I have fed to the system. H is the hidden representation right now. So probability of VH is equal to, we can define using this particular formula that says that E to the power minus energy of VH divided by all the possible U and G which are actually possible. All the possible hidden and representation. That is a very difficult thing because it says that all the possible cat images and their hidden representation. With respect to that, you find out that what is this bottom value, and then you are going to apply on this to find out the value. If you want to, but let's assume it is not possible to find out. Let me tell you that because all the possible cat images you don't have. But let's assume that if you have somehow, then what is the probability of this particular V? Probability of V means what is the probability that this image that I'm going to supply is of cat image. What is the probability that this image is of cat image? So for all the possible hidden representation which could be there for this particular thing, you find out the summation. This is called the marginalization. For all the values of the hidden that can take, you can find out the summation. This is a standard term called marginalization. It would be clear to you if I give you an example. So here is an example where a very simplified example where I have visible unit had two things, V1 and V2. Hidden unit had two things, H1 and H2. There is a connection -1. There is a weight 2 and 1. All right, what can I feed over here? Now, since it is a very small model, I can find out everything. Otherwise, I may not have find out that all possible things what I can supply to the system. So what is the input? All possible input 0, 0, 0, 1, 1, 0, 1, 1. These are the things that are possible to be inputted. So V could be 0, 0, 0, 1, 1, 0, 1, 1. In all the cases when it is 0, 0, I can see that what is the assignment of hidden unit 0, 0, 0, 1, 1, 0, 1, 1. So I am repeating everything over here. What is the energy into this particular place? Because you know that energy, everything is 0, 0, 0, 0, 0 assignment. You can find out that what is the energy. For example, here in this particular setting, it is 0, it is 0, it is 1, it is 1. So if you find out the multiplication, you would be able to see that -1 is going to be your place. Make sense? So this is -1 energy. Similarly, you find out energy on all the places. You can find out this table. Yes. E to the power -e, that gives you that because in this particular formula it was placed to the e to the power minus this, so you put onto the e to the power -e, you find out this value. The summation comes out with 39.70. This is the total summation that I need to put at this particular place. Okay, this is the total summation that I have to put at this particular place for all the possible things. So that's why I was telling that finding out this value is nearly impossible. But if I get it, I can use this value and divide into this particular value. I get this, what is the probability of with respect to a particular hidden representation. These are the 4 hidden representation possible for this particular value. I see that these are the probability. Now I have a summation. If I want to find out what is the probability of this particular signal, it is this, because I can find out the summation of all these things. So with this kind of weight, with this kind of hidden representation, the probability that this particular, most probably this is going to be the item. The probability is 0.664. So if I supply any cat image at this particular place, I can find out what is the probability that it is a cat. Sanyara? I can find out what is the probability that it is a cat. All right, challenge. Big challenge is this: how to find out this is very difficult. This table is very large. Finding out this value is nearly impossible. Very difficult to go ahead with. So there are problems. Now, I'm going to tell you a very simple thing that you would be agreeing that let's assume that I have a database. I told you that database has cat and dog images. For all the cat images which are there, I can find out what is the probability of that particular cat image. All these values should be higher. All these values should be higher. So if I multiplied by cat image 1 multiplied by probability of cat image 2 multiplied by probability of cat image and whatever the number of things which I have in my database, this number should be larger. Okay. So my objective function is going to be that I want to make this particular quantity for all the cat images, the probability that we have just computed, the probability should be higher. And for all the values, the value should be higher means what? The multiplication should be higher. If I multiply, the multiplication should be higher. Into the computer science domain, we don't like multiplications. So we can say that log of this quantity, if I take because if it is multiplication is higher, log is also going to be higher. We can apply a log. By applying the log, immediately my problem solves that this particular term by term summation, it becomes term by term summation. So for everything that was actually here with me, I can tell that here is a log of this particular quantity. I'm going to find out that summation of log of this particular quantity for all the things which are going to be fed to my network circuit should be higher. Okay. Okay. So as I told you that finding out for all the things when the number of units are large, we cannot compute the normalization term that is on to the bottom. So there is some idea that tells that a Markov chain Monte Carlo simulation kind of thing that you can apply, and by this you can somehow guess that what is the right value. Okay, estimate. Instead of guessing, I should say the estimate. You can estimate this particular value. Okay. So sometime thermal equilibrium that few minutes back we had talked about can also be utilized to find out these values. So ultimately, you want to update the weights. Okay, there are multiple weights. So we have defined that log of PV. This is the value that I wanted to maximize. Okay, so if you want to change a particular weight, simple thing. Find out what is the derivative of this particular term with respect to Wij. Any weight that you want to modify, what is that? What is the derivative? And this derivative would be multiplication of Si Sj with respect to the model and with respect to the hidden. Because here I'm telling that this is the hidden part, this is the visible part. What is this formula? Si Sj. What is Si Sj? Okay, let me tell you. It is again the same thing. Here. Here in this particular formula on the slide 1. Okay, I'm on the slide 1. Okay, if on this particular formula, if I say that find out what is the derivative with respect to the Wij, what would be the value? This would vanish. And only Wij is here. So what would remain? Si Sj. This is what the formula is. That for all the places where there is a Si Sj, all the places when there is a Si Sj, you find out their summations, multiplications, all the possible multiplication. By this, you find out that what is the change that I have to do. By this, you find out how much change you have to do. Using this thing, you can now modify the weights. And by this, you can apply some kind of learning. It is not the back propagation, please note. I'm not doing.
And how do you change the states?
State, you have to changing state is again I have not talked about anything about that. Okay, changing state, use this particular probability function and apply and change and evaluate that what is the value. There is no systematic way. From one state to another state, there is no gradient descent that can tell you that go change the state in that particular way. There is a probability associated with that probability. You change the states and evaluate that what is the value, and ultimately you would be able to reach to the smaller value. That is our understanding.
Trial error.
trial and error, and that's why training is very difficult. Now that is these things are problematic. If you can train them, you can see that the what are the thing they are offering. They are offering very good thing, but we cannot train it. That is a big problem. All right, so the basic idea of the Boltzmann machine is this: that you are going to settle with the data and settle with the no data. Means there are there are two phases into the training, and multiple number of time you are going to iterate, because you have to change the weight of W's multiple number of time using this is the same formula, na? That summation for all the things, and find out that how much you have to change using this probability thing. We have seen that how to find out the how much I have to change, and then you can find out and update the value. I'm not going to that detail. However, it is also not required. So now I'm going to talk another concept that is a very useful concept. Now let me connect you that what we are doing right now today these days. The idea a few minutes back we have discussed was called the Boltzmann machine. Everybody knows that. Now I'm going to talk about another thing that is called the restricted Boltzmann machine. What is restricted? Restriction is this: that things would be into one line only, and there would not be anything else that is connected like this. In between connection would not be there. Only independent units would be there, and they are connected like this, fully connected. This is a restriction. Now you cannot make the circuit any complex circuit inside. I have put a restriction. So now the capability of that model has been reduced. However, the important thing is this: that since it is connected to these things only, if I want to find out what should be the right state, so immediately in one step I can find out that they're only connected with that thing. They're only connected with this thing. So in one step I can find out all the things. What is the right answer? Okay, same kind of probability distribution I'm going to utilize to change the things again with the probabilities. But so it is nothing more than this. What is the probability that this is going to be 1? You can see the formula is this. What is the formula? You all know. What is the probability that it is going to be 1? There are weights. This weight need to be multiplied by these values, and then you apply into the sigmoid. Same formula that we were using, na? Because this is what the input is. V values are actually the input. They are multiplied with the weights. Weight is multiplied with the Wi multiplied by this. Apply a bias that is also added over there. Find out this value. This is going to tell that what is the probability that it is 1 or 0. This is the thing that we are doing these days. Make sense? A very interesting idea again comes that when we apply these kind of restrictions, what is the idea? Idea is this: that here you can draw another box from up, okay, and you can tell that let's assume that there is something that has these many number of bits, and you say that 3 bits are there. You can make a box. You can make another box also where 3 inputs are there and 4 outputs are there. 5 outputs are there. You can make another box where 5 inputs are there and 2 outputs are there. You can make another box there 2 inputs are there, 1 output is there. And if you can bring like that, then you can club them. Okay, you can do a short circuiting. You can do a short circuiting. Means what? That initially there is 4, then after that there is 3, then after that there is 5, 1, 2, 3, 4, 5, then after that there is 2, then after that there is 1. What is this? Can anybody tell me? Do you have seen this? Anytime have you seen this? This is the neural network that we are actually working these days. It is a restricted part. Using the restricted machines, these are the network that we are going to have. But here in the training, it is very important that at the time of training, you train this particular part first, then this part, then this part, then this part. So one by one, layer by layer training need to be done. It is called the stacking. And when you build the circuit, a larger circuit like this, it is called the deep belief network. It is called the deep belief network. That actually means that whatever network circuit we have these days. Okay. All these slides are with you. I would not go into that much detail. Again, the same thing that comes, that how to train all these things. This is not new. It is coming from the same formula that we have seen earlier, that the probability of a hidden unit being 1 or being 1 is going to be dependent upon the sigmoid function, and therefore you can update the weights like that. I will not go into much detail. That is also not much important. But the idea you should appreciate that it contains an energy. Using the energy, we can find out the best states. If somehow these things start working, we may be getting very interesting kind of circuits that are actually very near to the humans. Thank you very much. Thank you for the joining. If you have any question, please